that are made by plants, for example, like lycopene. It's kind of a reddish color. Do you know where you find lycopene? What's a nice red vegetable? Tomatoes, yeah, lycopene. Whatever. Tomato fruit, yeah, whatever. That's what I said. That's what my wife always says when she says something wrong. That's what I said. All right, so anyway, chromophore, beta-carotene. It's a, what do you notice that's kind of crazy about this molecule? It's got a massive, what we call conjugated pi cloud system, all right? This is a massive, very large pi cloud system, okay? So, it's got a conjugated pi cloud. Does everyone see that? So when you start way on the left here, you have a double bond and a single bond, a double bond, single bond, double bond, single bond. All right. So what we mean basically is that you could just move these, you could just shuffle electrons through the system. It's a giant resonance structure. These electrons could go here, these electrons could go here, and so on and so on. And this allows for many cool things to happen. Okay. One of the cool things that can happen is, for example, these are healthy foods, right? You always hear about beta-carotene being healthy for you, lycopene, yada yada. And these guys absorb free radicals. So a radical single electron can sort of delocalize over this long pi conjugated network. That's useful. And the other thing that's cool about it, which is more pertinent to what we're talking about now, is that these large conjugated pi systems absorb well in the UV visible range, so they have pretty colors. Okay. And you might say, well, why do vegetables and fruits and whatever have these kinds of dyes in them? Why do you think that's useful to them? Why? Well, that's okay. So the answer in the front is to attract animals to eat them. Probably, yeah, maybe, but also protect them from damage from UV visible light, damage from the sun. So you're protected when you have these pigments. And for the same reason, like I just said, you absorb you can scavenge extra electrons which are created when you shine light on things because you excite electrons, okay, in unstable configurations and create photo-oxidation products. All right. So we have a large system, and I already said, okay, it's orange because it absorbs in the blue. Okay, and it's absorbing in the blue so well because it has this huge pi cloud system. And it can do a lot of pi to pi star transitions. Okay, and so these pi to pi star transitions have an appropriate, we call energy gap between pi and pi star. This is an energy gap that is in the blue, violet, cyan, that sort of spectrum. So that is why if you look at an absorbance spectrum and you have here absorbance on the y-axis and you have wavelength or lambda in nanometers on the x-axis, and you go say from 200, 300, 400, 600. Has anybody read ahead in their notebook or lab manual where the absorbance max is for beta-carotene? No one's going to own up to it. Yep, 455. All right. Give her. See, you made me proud. All right. So 455 is the absorbance, we say the absorbance max. Okay? And that, like I say, that absorbance max right there is going to tell you, when you use that equation I just told you about, that energy band gap for those pi to pi star transitions. See, it's just as simple as that. You might say, well, why is it so broad? Well, that has to do with the fact that this thing's bouncing around in aqueous solution and all kinds of other things are happening. It's not just electronic transitions that are occurring. All right. Now, I will tell you one more thing, and it's not in my little note packet about light, which I think is kind of interesting. It's, people ask this question. What happens to that excited electron now? Does anybody have an idea? What could possibly happen? Well, it could release a photon. Now, I don't know how fluorescent beta-carotene is, but that's what fluorescence is. So if that electron comes back down from pi star back to pi, then it could release a photon and we'd see some color. Now, you can't see UV light, right? But has anybody been to a fraternity party that has black lights? Oh, wait, you don't go, oh, sorry. All right, I still get mileage out of that joke. So the reason you can perceive, black lights are putting out some UV stuff that you can't see really. And the reason that, your clothes light up is they have dyes in them. Like if white looks kind of a bluish purple, well, there's a dye in there that's fluorescing a purple color when it's absorbing invisible UV. So you absorb at a higher energy and then you fluoresce at a lower energy because we don't have any sort of perpetual motion machine in this process. Some of that energy is lost dissipatively through thermal losses, vibrations and so forth and so on in collisions. And so you lose some of this energy as it's fluorescing. We're not going to talk much more about fluorescence, but that is another way that electron, of course, the electron can just stay up there and just turn into a radical, just fly off. Okay, and now we've lost this electron, and that's how you get these oxidized products. All right. So what are the rules? Well, if you're in the UV visible region, then there are three major transitions to worry about. Okay, so there's pi to pi star, there's non-bonding to pi star to worry about, and I'm not going to really talk about non-bonding to sigma star today. No, I'm not going to talk about the third, but that's non-bonding to sigma star. But these are all appropriate. These are all appropriate transitions to think about. So we got pi to pi star here. We have non-bonding to pi star, and then we have non-bonding to sigma star. Okay. So 1, 2, 3. And the question I ask is, is non-bonding to pi star or pi to pi star going to be a longer wavelength? Which one is going to have longer wavelengths inherently? The longer wavelengths are going to occur with the lower energy, so these guys would have longer lambda here. Okay. Longer lambda than here, and this will have shorter. Okay. Shorter lambda for pi to pi star, higher in energy. Okay, so you always want to look at the band gap to determine the energy. Okay, so let's look at a simple example. Let's look at 1,3-butadiene. Okay, so what does that look like? Well, buta means there's 4, and then 1 and 3, we have, on position 1 and 3, we have enes, and enes are double bonds, so it looks like this. You can put the hydros on there if you want. Oh, no hydro there, Texas carbon. So if you look at this molecule, you can already eliminate some possibilities in thinking about what its spectrum might look like. And the first thing you'll notice is that it only has pi. It only has pi electrons. There are no non-bonding electrons, okay? There are no non-bonding electrons. It only has pi electrons. So if you looked at its spectrum, you'd see something like this. You'd see a single peak, okay? You'd see a single peak. And that's because it's dominated This is lambda versus absorbance. And that's because it's dominated by a single family of transitions involving pi to pi star. Okay? There's no other possibility because the other two involve n to n star, n to sigma star. Okay? But if you had this molecule, on the other hand, this, by the way, is something that will form on your breath if you happen to go to a fraternity party. It's acetaldehyde. It's acetaldehyde. Okay? Acetaldehyde is a breakdown product of ethanol. When it's not completely broken down to acetic acid, it goes an aldehyde in between. Anyway, it has pi electrons, right? We have a pi bond between the oxygen and carbon. So we have pi. Pi electrons are there. And it has non-bonding. Because there on the oxygen, we have non-bonding. So we have non-bonding electrons here, we have pi electrons here. And if we were to look way, way down in the UV for this guy, because of course it's not a very big conjugated pi system, it's a very small system, then it's going to absorb way down in the UV. And we'd expect to see a couple of peaks, okay? We'd see a peak corresponding to pi. And which would those be? Which peak would that be? The first peak or the second peak for the pi electrons? Who thinks the first peak? One guy. He's taking it back. Wow, this is like Plato's cave. This guy's right. Yes, these are the pi electrons. And you guys all thought he was crazy, but I think he might be. No, I really put him in Plato's cave. All right, I'm just teasing. I'm teasing. I love you. All right. So because there's pi electrons and there's non-bonding electrons, then you'll be able to have, you'll be able to have n to pi star, and you'll be able to have pi to pi star transitions. Okay, so you get two peaks. All right, on your UV vis absorbance spectrum. Okay, so see, you can already now do basic spectroscopy with these simple rules. Okay, so those are the rules. There are lots more rules. If you get deeper into organic chemistry, you can think about all the functional groups you put on these molecules and how those functional groups will perturb the spectrum one way or the other. Okay. All right. Oh, I don't have to hit that button. Okay, so now this leads us to the Beer-Lambert law, which we got to cover here really quick. So we can do a clicker question. So Beer's law, which everyone should know already, I hope. Absorbance equals epsilon, or the extinction coefficient, times L, the path length, times C, the concentration. Okay. So we got absorbance. Absorbance is unitless. There's no units on it. Technically, what absorbance is just a logarithm of the intensity of light divided by the intensity of light when there's no sample in there, or the blank is in there, okay? So when you're taking the log of an intensity over intensity, that becomes unitless. Of course, the log of unitless number remains unitless, and you shouldn't take the log of united numbers anyway. And then you have the extinction coefficient. The extinction coefficient. That one you may not have heard of. And extinction coefficient has units of per molar per cm. And well, that's good because you need to deal with the fact that you have path length, which is in units of centimeters. That's the length of your cuvette, or the light path. And then you have good old-fashioned concentration here, which is in units of molar. So path length, here's a cuvette. A cuvette is a fancy rectangular box that contains, this is a cuvette, C-U-V-E-T-T-E, and that contains your sample. The path length here is generally speaking 1 centimeter, although you could have really skinny cuvettes that look something like this, and you could be 1 millimeter. Okay, so depending on what kind of cuvette you have different path lengths. So basically what your spectrophotometer looks like is you'll have your cuvette, and inside of that you'll have your sample. And if we're really cool about it, it'll be beta carotene. Does everyone want to eat some carrots when they get back? No. Okay, the light source goes through, okay, the sample. Now, I shouldn't have done that. Let me get my eraser here. Let's create the light source here. Here's your light source. Okay, your light source is going to shine photons, which are the whole spectrum, onto what we call a diffraction grating. Diffraction grating is going to be able to pick off, depending on the angle that you hit this at, different colors, okay? And so, you'll be able to move this diffraction grating and then get different colors. And so this will ultimately select your lambda that goes through. And then on the other side of the sample, you will have a detector, which we sometimes call a photo multiplier tube. And it's a photon detector. Detector. I spelled this terribly wrong here. I butchered it. I'm trying to hurry, and then I start to make... God. Anyway, it's a photon detector. Okay, photon detector will count photons that hit it, turn that into a voltage or a number of counts, and then you'll be able to determine your absorbance. That, in a nutshell, is your equipment. And we have a few minutes left, and we will do a clicker question. I'll fire up the clicker system. Hopefully you were paying attention. And okay, so here it is. Let me move this thing out of the way. Okay, which molecule fits the given UV visible absorbance spectrum, all right? So this is all the information you'll get. You have this absorbance spectrum, and hopefully it's obvious enough what the key feature of that absorbance spectrum might be. Talk amongst yourselves if you like. And then on the bottom here are 3 different molecules, and you have to decide which molecule would best fit that type of spectrum. Look at these people chiming in here. Still going strong. Hey, you have a 33% chance here. Any last minute stragglers? I want to show the answer so everyone can go to the next class. Still going in. Choose wisely. Okay, all right, last one. Is that it? Good, 408 of you. All right, I stop. Let's see how you did. Okay, that's pretty good. A little bit of confusion there, though. Pretty tough question, huh? All right, let me just show you. Okay, let me see if I can just get out of this presentation mode here. And okay, here's the answer. Huh? Why? Oh, there we go. So there's two peaks. Okay, see that? Two peaks. That means you have both pi and non-bonding. Okay, because it's in the visible range. All right. It's a UV visible spectrum, and there's only one molecular system up there that has non-bonding electrons, and that's B, because it has a halogen, and halogens have 3 pairs of non-bonding electrons. So that's the answer.